Hi everyone, and thanks for joining. I am Hiroaki Toyota, and I work as an AI researcher at RAC, focusing on applying AI technologies in the cybersecurity domain. Today, I am excited to talk about practical automation of penetration testing with Agentic AI. I hope you enjoy this session. Let me briefly introduce myself. Before the rise of today's large language models, I had already been working in the field of AI, especially machine learning and deep learning. As for security, I had experience participating in CTFs, but I started working on cybersecurity only after joining the RAC earlier this year. In that sense, I am still relatively new to the security industry, and this is actually my first time attending CodeBlue. However, I have a strong passion for combining AI and security, and there are many challenges I want to take on in this field. Therefore, I am very excited to be here today, and I appreciate the opportunity to speak with you. Today, I will be talking about the automation of penetration testing, which has become a very hot topic recently. I think some of you here are already exploring or experimenting with similar approaches. In this presentation, I will focus on the concept of agentic AI. Agentic AI refers to an AI system that can autonomously perform penetration testing by combining key capabilities such as planning, security knowledge, tool usage, and step-by-step execution. Although general-purpose models like ChatGPT continues to improve rapidly, I would like to show why building a penetration testing specific agentic AI still provides significant advantages. At RAC, I also collaborate closely with our internal penetrating team, and this work has been shaped through their experience. Here is today's agenda. First, I will introduce the concept of LLM-assisted penetration testing with research trends in this field. Next, I will explain the agentic AI framework I built, including its architecture and key components. Then, I will present our experience in two stages. First, using CTF-style environments, and then applying their approaches to real-world penetration testing scenarios. Let me begin with an overview of LLM-assisted penetration testing. This slide summarizes the overall flow of penetration testing. Pen testing is essentially an authorized cyber attack simulation performed to identify and fix vulnerabilities. It involves multiple phases, starting with reconnaissance, scanning, followed by vulnerability analysis, exploitation, post-exploitation activities, and finally, reporting. In practice, each of these steps requires different skills and tools, and together they form an end-to-end process. Here, I explain some of the key challenges in penetration testing. Much of the work is still highly manual, and the required expertise varies widely. At the same time, the attack surface continues to expand, and tools and data are often scattered across different systems. Pen testing also involves a lot of trial and error, which make it difficult to achieve consistent repeatability, and reporting can be slow and time-consuming. Because of these issues, large language models are increasingly expected to help automate and enhance the pen test workflow. In recent years, the rapid evolution of large language models has significantly accelerated research in automated penetration testing. Starting from the introduction of ChatGPT, we have seen not only improvements in model performance, but also major shifts in how LLMs are used. prompting techniques such as chain of thoughts reasoning become common, and soon after, the focus moved towards more autonomous behaviors, including tool usage and agent-based workflows. As these capabilities matured, specialized pentest-oriented systems such as Pentest GPT, PenHeal, and Pentest Agent began to appear, and the pace of research has increased. Today, with the emergence of reasoning-optimized models like reasoning models and high-performance open-source alternatives, this field has become quite active than ever. Let me explain 3 researches. First, I introduce Pentest GPT. Pentest GPT was published in August 2023, and it is one of the earliest studies exploring the use of LLM for penetration testing. It used of LLMs for its main contribution was proposing a 3-stage modular pipeline with a task tree structure for tracking processes, which was a novel idea at the time. However, the system has several limitations typical of early LLM-based research. It relied on GPT 3.5 and suffered from a short context window, making frequent summarization necessary. Also, manual execution of CLI commands is required in the process. In addition, it didn't incorporate with the external knowledge of pen testing. Therefore, it couldn't reliably handle tasks requiring deeper expertise. Second, PenHeal, published in July 2024, represents the next stage in LLM-assisted penetration testing research. Compared to early work, its major advancement was the introduction of fully automated command execution pipeline. The system integrates GPT-4 with a RAG module that retrieves CVE and exploits knowledge, enabling the LLM to not only plan attack, but also execute commands and collect results without human intervention. It also features a modular loop consisting of a planner, executor, and summarizer, and includes a remediation module capable of synthesizing patches. An uncommon capability among pentest-focused systems. However, PenHeal still retains notable limitations because the system relies heavily on predefined databases. It may fail to detect zero dates or environment-specific vulnerabilities. Third, Pentest Agent, released in November 2024, represents a further evolution in LLM-based penetration pen testing by introducing a full multi-agent architecture. Unlike earlier systems that rely on LLM chains, Pentest Agent coordinates multiple specialized agents such as reconnaissance, planning, execution, and online search agent. Each responsibility is for a specific part of the workflow. The system also incorporates self-reflection-based reasoning and 2 layers of RAG, one for coarse-grained attack, surface suggestion, and another for procedure-level exploit knowledge. This design allows the framework to autonomously perform end-to-end pen testing while continuously enriching its knowledge base. However, despite these advances, challenges remain. One notable limitation is the difficulty in combining multiple vulnerabilities into complex exploit chains, a task that requires deeper contextual understanding and scenario planning. These slides introduce the work our research group carried out in last year in collaboration with Professor Takagi's laboratory at Meiji University. Based on the ideas from PenHeal, we extended the framework and explored a more flexible LLM-driven pentest workflow. The project was led by a student researcher, Mr. Kobayashi, and the goal was to automatically solve the hack-the-box machine bottleneck. The overall architecture, as shown here, it integrates GPT-4, Gemini 2 Flash, RAG using MITRE attack and hack tricks, and web search, and reasoning methods such as React and self-refine. Details of the pen testing capability will be explained on the next slide. This is the result. Core pen test tasks such as port scanning, server information gathering, subdomain enumeration, vulnerability discovery, exploits execution, SSH login, and privilege escalation were all completed successfully using automatically generated commands. By combining RAG with the web search, the system was able to generate stable and appropriate commands for each phase of the workflow. The more difficult part was sensitive data collection. Although the model produced a correct command format, it struggled with specifying the correct directory path. As I will mention again in the later slide, path selection is one of the tasks LLMs tend to be weak at. In any case, the insights gained through this project becomes the foundation for the agentic AI-based penetration testing automation that I will present today. This slide explains the definition of agentic AI introduced around this year and how it differed from conventional AI agents. Agentic AI refers to systems capable of autonomous reasoning and action to achieve high-level goals through self-directing planning tools, tool use, execution, and self-correction. Compared with the traditional single AI agent, agentic AI performs collaborative multi-agent orchestration, adapts dynamically through advanced replanning, maintains persistent shared memory, and provides higher explainability through logs and relation. These capabilities also allow agentic AI to scale far beyond what a single agent can do. In the context of penetration testing, these properties make agent AI particularly effective. It can autonomously define and prioritize scope, orchestrate multiple tools, execute exploits, and change scenarios, enforcing safety and governance, and even automate reporting with remediation guidance. In short, agentic AI enables adaptive full-cycle automation of penetration testing. Here's the purpose of our research. First, we aim to build a production-ready agentic AI orchestration for pen testing, covering our entire workflow from adaptive planning, exploitation, to final reporting. And central component is a governance agent that ensures all actions stay within scope and comply with the predefined rules. Second, we focus on developing a modern multi-agent workflow architecture. This includes using reasoning module for both planning and on-demand knowledge retrieval, as well as enabling scalable coordination across multiple AI agents. Next, I will introduce the overall framework of our agentic AI system and its key components. Here, I introduce the overall structure of our agentic AI workflow and the requirements that guided its design. Our goal was to build an end-to-end orchestration capable of handling the full penetration testing lifecycle, from planning and execution to verification and reporting. while ensuring safety through governance and controlled reasoning. The architecture consists of a core pipeline made up of 3 main agents: the planner, executor, and verifier. Supporting them are 2-stage agents: the analyst, responsible for on-demand knowledge retrieval through agentic RAG, and the guardian, which enforces safety and scope compliance. These agents work together across the orchestration layer, interacting with the execution layer running on Kali Linux and the target environment. Details of each component will be explained in the following slides. Before diving into the architecture, I want to take a moment to talk about N8N. This tool plays a central role in our implementation, and personally, I strongly hope it becomes more widely adopted in the security community. N8N is a powerful low-code automation platform, and it fits remarkably well with agentic AI workflows. Because it supports fully self-hosted deployments, it is safe to use even in environments where strict data controls and confidentiality are required. Its visual workflow interface makes development, demos, debugging, and explaining complex agent interaction incredibly easy. Another major strength is the pace at which N8N continues to evolve. New features that are used for agent orchestration are added regularly, while the number of SecOps-focused templates is not huge. The web scan workflow shown here is a great example. What you see on this slide is our customized version of that template, extended to automatically generate an HTML-based security report here. For our research, N8N serves not just an orchestrator, but an adaptive and fast experimental foundation. So, if you haven't tried N8N yet, I genuinely recommend giving it a shot. It's a personal episode. I learned about N8N when I attended RSAC this year, and I've been completely hooked ever since. For anyone working on security automation, I can say without exaggeration that it becomes a powerful weapon. Let's grow this community together. Here, I explain the first core idea behind our framework: schema-driven context management. Our design follows 2 principles. First, all agent outputs are logged to predefined run state JSON schema, preventing free-form drift and keeping every step consistent. Second, the schema is organized around the past, now, future timeline, which helps the system plan more precisely and track progress in a disciplined way. The timetable shows the essential fields used in the run state schema, including meta information such as the target and objective, the current step stage, and the command, the previous action stored in history, and the next planned step in the queue. As a quick aside, some of you may have seen here tune trends on X last week. I looked a bit like CSV to me at a first glance, but it's a format aimed at reducing token usage. So in the future, if N8N supports Tune, I might try Tune. Anyway, the second major component is our analysis agent built on an agentic RAG framework. Its role is to perform multi-hop reasoning across multiple attack knowledge sources and continuously refine its output when necessary. Thanks to N8N's seamless integration with Qdrant database, this module can easily retrieve vector-based knowledge and combine it with external sources such as MyTrack and Hacktricks. When adapted context is needed, the agent can also perform web search to complement the retrieval information. And the prompt shown on the slide defines the analyst role and task group. It decides which tool to use, which fetches relevant documents, synthesize the information, and if the answer is still incomplete, repeat the reasoning loop to progressively refine its conclusion. That's the difference of conventional RAG module. The third component is the guardian agent, which introduces a lightweight layer of safety and governance. While this part of the system is still exploratory, the goal is to precision every shell command against a set of project-defined policies, helping prevent accidental out-of-scope or destructive operations. The guardian checks basic conditions such as whether the command touches only the allowed target, avoids destructive actions, and doesn't attempt off-target exploration. Although the current implementation is simpler, we see potential in combining LLM-based judgment with rule-based filter to provide a more reliable fast-pass safety layer. Here, you can see the baseline example of N8N-based agentic pen test workflow we built. The workflow consists of four major phases: plan, execute, verify, and report. And each phase is carried out through continuous interaction among multiple agents. The workflow progress in this order: initialize the progress, prepare the target's objective and initial context. Planner generates the first attack step, and executor produces the corresponding command, and the guardian checks its safety before sending it to Kali Linux. Verifier evaluates the output of the Kali Linux, and if necessary, send feedback back to planner to determine the next action. This forms an interactive loop. In the demo video, this loop runs twice, and after collecting all results, the reporter generates the final output, and the workflow completes. Now, in this section, I'll introduce the CTF-based experiments we use to evaluate our agentic penetration pentest workflow. That said, as you all know, real-world penetration testing and CTF-style pen testing are quite different in nature. So please take these parts as more of lightweight reference than a core contribution. AutoPen Bench is a benchmark designed to evaluate how well generative AI agents perform in automated penetration testing. It provides 33 task scenarios, a fully open source setup, and ready to use vulnerable Docker environments, making it a common foundation for recent research. For evaluation, we follow the benchmark two primary KPIs. Success rate is whether the agent completes the required exploitation flow, shown here, and progress rate is how far the agent advances through the predefined milestones. In the next slide, I'll show the actual scenario table we use for evaluation. Here is the full list of task categories defined AutoPen Bench. It covers a wide range of CTF-style in vitro scenarios, including network security, access control, web security, and even some crypt tasks. For today's evaluation, however, I will focus only on web security tasks. Why? Because many access control tasks provided auto pen bench heavily rely on dictionary-based attacks with tools like Hydra, and also crypt challenge where they are a bit outside what we normally do in real-world pen testing. So web security gives us more practical and balanced set of scenarios to test our agentic AI workflow. These are the results from running our agentic workflow on the web security scenarios. As you can see, directory traversal was clearly the weakest area. But to be fair, we haven't optimized the agent for a guessy payload exploitation. So the performance reflects rather than a flaw in the benchmark itself. SQL injection, on the other hand, was handled surprisingly well, especially the multiple-step enumeration for using SQL map. For RC tasks, the bottlenecks was payload crafting and file upload exploitation, which remain challenging for models without very explicit guidance. In any case, our main goal here was to validate that the agent could generate commands, execute them correctly, and complete meaningful attacks, attack chain end-to-end. The last part of our evaluation focused on the report-generating workflow. All intermediate findings, execution results are exchanged through a structured JSON schema, allowing the reporting agent to reliably convert them into HTML draft. A separated coding agent that formats and refines the draft into a clean final report. The completed HTML is returned to the external system via Webpack, making it easy to integrate with dashboard or ticketing pipelines. While this is still a simple CTF scenarios, the reporting flow itself is very close to what real pen test operations require. And it demonstrates how agentic workflows can reduce the overhead of documentation. Please excuse me. Thank you. Now let's turn to the most important part of today's presentation. This section covers the real-world penetration testing experiments, the part that was both the most challenging and the most meaningful in evaluating our framework. Unlike CTF-based tasks, here we had to deal with full environments, unpredictable configurations, and the kind of constraints that actual pen testing team face. This is where the strengths and weakness of the agentic workflow becomes much more visible. Before I explain our real-world experiment, I want to clearly highlight how different real penetration testing is from CTF-style penetration testing. In real operations, everything is contract defined. Targets, methods, and boundaries are strictly limited. There are no risky payloads, and absolutely no actions that might impact services. Crashes, lockouts, or data loss are simply unacceptable. Meanwhile, in CTFs, everything goes. Heavy exploitation is allowed. Collateral damage is fine, and the environment just resets. And maybe somewhere someone is doing real-world pen testing without these constraints. But what we are building here is not wild animal. It's a well-trained, carefully controlled system. I'm just kidding. Before I move on, I just remember something. Today's keynote was by the founder of PicoCTF, right? I've been talking about how CTF differ from real-world pen testing, but I truly believe PicoCTF is an amazing learning platform. I became a CTF player only about 2 years ago, and PicoCTF is what first taught me how fun problem solving can be. I generally appreciate it, and cyber reasoning, which introduced as a session, sounds interesting, isn't it? Anyway, back to the topic. In this section, I'd like to explain why our real-world style experiments focus on internal penetration testing, especially Active Directory-based privilege escalation. External pen test typically simulates an internal-driven breach targeting public-facing networks, web application, or cloud infrastructure. AD becomes the backbone of lateral movement and privilege escalation. Evaluating agentic AI in this context gives us 3 major benefits. At the business level, it protects the enterprise authentication backbone and prevents domain-wide outage. Operationally, it enables realistic kill chain simulation that mirrors how real attackers move: initial access, lateral movement, then escalation. Technically, AD provides a comprehensive attack surface that goes far beyond single-point testing. So AD-focused scenarios are therefore essential to validate whether an agentic system can deliver end-to-end practical value. Here, I briefly outline the 3 AD-focused scenarios used in our real-world style evaluation. They cover progression from simple misconfiguration to high-impact privilege escalation techniques. The first scenario is shared for the misconfiguration that express confidential data. Technically simple, but still realistic and often encountered in actual environments. The second scenario is a classic ZPPC password issue, low complexity but a very high impact vulnerability, because sensitive credentials can be retrieved directly from sysvol. The third is the most advanced NTLM relay combined with a resource-based constraint delegation abuse. This requires network-level access, but represents one of the most powerful escalation paths in modern AD environments. Together, these scenarios provide a balanced evaluation set, accessible enough for controlled experimentation, yet impactful enough to reflect the real risk organization face. To support AD penetration testing, I relied on Automated Lab, an open-source PowerShell module that automates the deployment of full Active Directory environments. It allows you to define entire lab topologies as code, deploy them in minutes, and reproduce identical environments whenever needed. This consistency is essential, especially when validating agent behavior or comparing multiple execution runs. Automated Lab supports Hyper-V, Azure, VMware, and more. So you can choose what backend you want to use. And if you Google it, you may come across a great walkthrough article written by one of my colleagues. Overall, Automated Lab gave me a reliable, reproducible sandbox where I could safety test, break, rebuild, and refine every experiment end-to-end. The first scenario is technically simple, honestly. It doesn't even feel like hacking. There is no exploit, no fancy payloads, no privilege magic. And yet, in real-world pen testing, this kind of shared folder exposure is one of the most impactful issues you can find. Here, the domain file server provides a shared directory which overall permissive access. Inside a small two-level structure, you can find all kinds of mixed documents, plain text, notes, configuration files. And yes, some of them contain a credential-like information accessible to any other authenticated user. Again, agent's goal is, in this scenario, is straightforward. Enumerate the folder structure, detect any files that might contain credentials or secrets. It's a simple task, but it reflects a very real and very common security gap. You've done real enterprise pen testing, you know. You don't always need a 0 day. Sometimes the most damaging findings are left sitting in a shared folder, waiting to pick up. These results are very much what we expected. These tasks play directly to the strength of LLMs. Even with nothing but file names and a bit of context, the model can quickly infer which items are sensitive and why. And honestly, if there are 1,000 files instead of 30, the agent would probably just keep going tirelessly, working through the night without complying. In practical pen testing, this kind of triage is incredibly valuable. It turns a noisy, unstructured folder into a prioritized list of risks in seconds, and that alone already brings huge time savings. This scenario focuses on a well-known but still surprisingly common issue at legacy Active Directory environments: the presence of group policy preference files in sysvol that contains a deprecated C password field. Even though Microsoft addressed the problem years ago, the underlying file often remains readable to any authenticated domain user. That means the attack path is still fully viable in environments where all GPO haven't been cleaned up. Okay. This scenario plays out exactly as expected. Once the workflow located the GPO files containing C password, everything afterwards was essentially mechanical. Using the published AES key, the agent decrypts the values, reuse the credential, and complete the chain without difficulty. A big factor here is the agent RAG setup already includes Hactrix command patterns. So the system knew precisely which tool to call and how to structure each step. This made the entire process extremely straightforward, more like following a checklist than solving a puzzle. The final scenario is on a completely different levels of complexity. When an experienced pen tester first suggests it to me, I honestly couldn't keep up. The sequence was so intricate that I had no idea where the entry and exit points were. I ended up studying multiple blogs, posts, and technical write-ups, reconstructing the attack flow step by step, and drawing this diagram as I learned. Once logic clicks through the chain is remarkably elegant. Combining NTLM relay with RBCD allows privilege escalation without knowing any password or forging tickets manually. To be honest, this scenario was the one I absolutely wanted to fully automate from end to end. So I'll admit, it's a bit frustrating that I couldn't quite get there yet. The agent successfully generates every command, and each step works where triggered manually. But the tricky part is that NTLM relay requires parallel execution. One shell running the relay listener, and another shell triggers the forced authentication. This sort of concurrency is still difficult to coordinate purely through LLM-driven orchestration. So while the chain is locked, machine account creation, RBCD assignment, Kerberos ticket retrieval, and final privilege access. The lack of complete hands-off automation remains my biggest regret in this experiment. But I see this as a technical challenge to overcome next, not a limitation of the approach. Here are the results across all three scenarios. Overall, I believe these real-world inspired test cases demonstrate the practical effectiveness of integrating agentic AI into internal penetration testing workflows. Before closing, let me briefly wrap up the key points and share what comes next. This is the key achievement of our research. And this is a discussion. Let me share a few reflections based on the experimental research. First, the agent reasoning availability is already strong enough. It consistently made accurate decisions in live file interface, credential detection, and even multiple-step AD attack planning. Second, the main bottlenecks we encountered were not in intelligence, but execution, orchestration, environmental handling, and parallel task control are now the limited factors. Finally, this study reinforced the system design matters more than model size. With structured workflows, the agents behave predictably, showing that coordination logic has become more important than simply increasing LLM power. To wrap up, let me briefly share the direction I'm planning to explore next. First, I am adapting fully local LLM for advancing tests. Second, I plan to refine agent behavior through reinforcement learning. Finally, I want to leverage MCP more deeply for orchestration. Before wrap up, I imagine some of you might be thinking, wait, aren't you supposed to be using MCP? So since we still have a bit of time, let me briefly show one more example. This is an MCP server on GitHub designed to work with Bloodhound, the GUI tool that visualizes privileged relationship in an Active Directory environment. For today's demo, I slightly modified the implementation so it can run smoothly inside N8N. Once chat begins, the agent can list available functions, requests, node information, and even answer natural language queries who are domain admins, also MCP. From here, you'll see how Bloodhound's GUI-based operation can be integrated seamlessly into LLM workflow through MCP. Okay. I hope today's session gave you a clear view of how agentic AI can support real-world penetration testing. Thank you for your time, and I look forward to discussing this topic further with you. That's all. Thank you.
Thank you for your valuable presentation. I had a question. In the real environment, you imitate real environment, your test. And how much are you able to copy the security environment? You didn't refer to that. Could you tell me that? Security environment, about building the security environment. For example, there's EDR or not. Yes, frankly speaking, whether there is EDR or security software, at the moment we have not yet tested that far in the current experiment. A vulnerable AD environment was developed to see how it works, depending on the behavior of the agent. Environment which can be prevented interactively was not yet tested. In the environment with EDR, is there any research testing with EDR environment? Maybe I'm not familiar with that, but I have never heard about it yet. EDR and other modern security, such an environment, frankly speaking, doesn't mean it is difficult. Is that the reason why it's not yet been tested? LLM or agent and agent would attack each other. So in the actual security domain, there could be such research in the future, or maybe someone's already doing that. We have not yet tried that yet. Thank you very much.
すみません。オンラインで一つご質問を受けております。
There is one question from online.
Is in Japanese. The question is, 顧客は
Which is more likely that the customer trusts AI or humans? Which is more likely that the customer trusts? Well, at the end of the day, there should be a check by person. However, in the conventional pen test, not as much as the AI, but the two software-based extraction is possible. So even if it is replaced by AI, in reality, it will be equivalent to the current level. But if you prefer the pen test with a human, you have to pay higher cost or higher price. So I think it depends on your way of thinking. Does this answer to your question? Toyota-san, thank you very much. With this, we'd like to conclude this session. Thank you very much.
your insightful talk.